If the microphone is muted.
I'm muted since the beginning. It's not changing. Huh? Can you take it out? Are the slides are not changing?
Now we can hear.
Yeah, the microphone is. You have to switch your microphone.
Now we can hear.
Mas isto está desligado. Not going into slideshow for some reason. No? Yeah, I'm just started again. It doesn't. Okay. Does it change the slides or not?
You're seeing the PowerPoint itself.
Why is it doing differently than before? No, no.
Não, vá lá esse
Este? Na verdade tem estes três abertos.
Não, é este.
This one. It goes into... Does it change? Is it changing to slides or not?
Zoom, yes. YouTube, yes.
Okay.
Yes.
Okay, thank you. So it's good that I was the one with problems. So as I said, I'm going to this presentation. I'll go following these structures. I'm going to first present the research problem and goals. I will then go into a bit of state of the art on diversity and co-design, generative design systems, and representation and visualization. And then I'll go into the tool itself that we have developed, my changes, and then I will end up with this discussion and concluding remarks. So the research problem that we bring here, in theory, architects promote a participatory approach, as been said here before, also by our keynote, that gives inhabitants the power to co-determine architectural design. So we want to ensure architectonic quality, and we also want to ensure the inhabitant satisfaction. However, architecture also advances the authorship position that consists on maintaining the architect's concepts and decisions when refurbishing or altering houses. And this can mean, of course, that no changes are allowed or only those that architects sanction. And this brings a paradox in architecture that I'm going to follow during this presentation. So this is just a nice drawing. Everyone, I think, here knows the Corbusier domino. We are very used to this design, to this open building approach, to leave the rest for the inhabitant. But when we see the customizations done in the other 3 drawings, then we sometimes have some doubts. Is this what we envision with the open design? And then we start questioning what is indeed the possibilities of inhabitants to customize their designs or their houses. So the goals of this work are to present and assess tools that support a strategy for architectonically responsible housing personalizations. And the tools that we bring here are first, for defining and visualizing architectonic modifications of existing housing in co-design projects with inhabitants. So we want to bring these tools to inhabitants for them to do modifications after the construction. So those modifications can be done because the regulation changed, because there's the need of updates, because lifestyles have changed, because families have changed, and then some needs are to be included. And also tools for enabling inhabitants to understand and explore modifications of their houses. So not just enabling those modifications, but also being able to visualize them and understand exactly what they are doing. Very briefly going through an overview of work being done into these fields. So as you know, diversity and co-design has been research done for decades. With the work of John Bracken, for instance, in urban buildings in the 60s, to now new approaches also on incremental design, both by Reinhard Gother and by Elemental Practitioner Office, and also in a different context, the solutions of MVRDV for middle class housing. In the scope of generative design systems, also Edward came and spoke on these topics. We have generative design computers tools that have been developed to respond to the need to create alternatives of design. We can generate with these solutions houses or solutions in one go, input needs, output a design. We can also design those step by step, depending on the systems that we have implemented. They are still not very much brought to the real life design to the inhabitants or to be used in real life design processes, but nevertheless they exist and they have been researched these last decades. And the last topic that we bring is in the scope of visualization and representation. So in architecture, we have been using for long bidimensional floor plans, elevation sections. And for us, the code of representation is obvious. We use them, but they are difficult to read by non-architects. So what we use now also are the virtual and augmented environments. And those tools, we believe, it's our assumption, those are tools that enable inhabitants to understand better the designs by being more immersive and enabling more interaction. So we have been developing tools. We now present in this paper My Changes. So My Changes was created by some thinking on Malagueira regional plan. Just a brief introduction. I think that most of you know what is Malagueira. It's a housing complex that was built in Portugal in the 70s by a very known architect, Alberto Vieira. So the original plan is what you can see on the left. And what is happening now is on the right is that inhabitants have made several customizations. And bringing back what I said in the beginning about the paradox in architecture, although we recognize as architects that houses can be customized and it's obvious, what happens in reality is that sometimes when we look at these customizations, we feel that some architectural value is lost. So the first stage of this work was done 2 years ago in 2018, and the idea was to develop a post-handover shape grammar that would introduce the inhabitants' wishes in the transformation of individual houses. So we had a big sample of transformations, and we include that in a shape grammar to see how the changes have been occurring and what could be brought to the inhabitants to customize their house in the future. And the stages after that one are the ones that we bring now in this presentation and in the paper. The first of them is to develop a mock-up interface for my changes. So how can we present this to an inhabitant? And then to develop different modes of visualization, more or less immersive, tools that can be more or less, or can show more or less visibility to the surrounding areas of the house. And then we wanted to test my changes tools with real inhabitants. So we are focusing on validating these design claims. So we presented them to inhabitants and test them. We're going to present that later. So my changes has two main parts. One is the shape generation, and the other one is the visualization. So we created this mock-up to simulate some of the generation possibilities of the grammar. So this is a mock-up, so it doesn't generate everything, but we created something that can generate some alternatives. The alternatives are based on the facade of the building. So an inhabitant can use this mock-up and change or customize the walls, the outside walls, the doors, the windows, the gate, and the ornaments that are visible in the facade. The second part of this tool is related to the visualization. And we tested 3 different types of visualization. One based on a non-immersive screen, a tablet device, where the user can see the final design as a static image, as the one that is presented in this slide. The second one is a semi-immersive visualization, and then the user can use a smartphone. And this smartphone can be in an interactive way. We can see a 360 degrees render of the site, so we can visualize everything around. So it's more immersive. And the third option is by using a head-mounted display, and then we can really freely navigate into the design. So we can approach the house, go away, go around the block, so we can take a lot of time and do the visualization in a very fully immersive way. So we then brought everything to the field. We went to Malagueira, we interviewed several inhabitants, and what we wanted to know was how satisfied users were with such a customization tool. So the first part, the generation part, and how they were satisfied with the modes of visualization. So from less immersive to more immersive. We had a sample of 12 inhabitants, so not that much. So we are still aiming at extending this experiment and having a bigger sample of inhabitants. And the average age was 59 years old. That's also very representative of the population living in this neighborhood. Of course, also representative of the time that we were there. And so everything has to be extended. And we divided our questionnaire in 2 main topics. One was to assess the usefulness of my changes. So we wanted to know, for instance, if inhabitants would think that this tool would be helpful to change the outside of the house. So all these questions are ranked in a scale from 1 to 5. This was a positive answer. So most of them, 4.33, said that indeed this tool would be helpful to change the outside of the house. We also wanted to know if inhabitants would use this tool to customize the outside of their house. And again, it was a positive answer to this question. And this question now, we asked if they would like to use my changes alone or with the family. And this, I will be back to this question a bit later. They said yes, that they would like to use the tool. So the idea is that you, in a way, kind of play with this tool. This is almost like a game that you can rehearse different possibilities of customization. And the hypothesis that we had was that person can be at home playing with the tool and trying to see what are the options to customize the house. And then we also wanted to know the satisfaction of users on using the interface of my changes. So in this case was more related to the visualization possibilities. So we wanted to know in which way of looking at the changes did the users preferred. And this was also very, very, in a way, surprising, also by the average age. So the answers were divided in two main. Lots of people, or kind of half of the people, prefer to see it in the tablet device, static image, and the other half more or less prefer to see it in the head-mounted display. But we wanted to know also why, because also these questions sometimes are so difficult to assess. And answers were the ones that preferred the tablet. Most of them said it was easier and simpler to see. So yeah, I just see the facade. And the other ones who chose the more immersive virtual reality mode, they said that, yeah, this looks real. So in this way, I can indeed understand everything. Very relevant also if we consider the age of these inhabitants. So we were assuming that probably they would not like that much the head-mounted display, but nevertheless, the answer was very positive on that. Another question, we wanted to know which way of looking made you better understand the house. So it's not just fun to try out to navigate in a virtual reality environment. We wanted to know exactly, do you understand, do you not understand? And in this case, also the responses were divided into two. So some people preferred, again, the tablet, but more now preferred the head-mounted display. Of course, again, the sample is not that big, so we have to extend these studies. We also wanted to understand if people consider to be important the understanding of the entire street when customizing their house. So in these three modes of visualization, the first mode, the static image, does not give or does not bring the entire street to the person. He also only considers his own house. But most of the people said that indeed, looking at the entire street, it is important when you want to customize your house. And then we asked, and this is the question that in a way or contradicts or complements the previous question. First, we asked the inhabitants if they wanted to, or if they would like to use the tool alone. But then we asked them again, would you like to use it alone, or would you like to use it next to a professional? And then the answers were really divided. So it was not clear, again, 12, the sample of 12, it was not clear. Some people preferred to use it with an expert next to him, and others would prefer to use it alone. So this is also interesting question to explore more in the future. And the last question was, we asked inhabitants if this tool should control the changes to the houses. And let me give a brief context to this question. Malagueira has very strict rules. So indeed, everything that is happening now in law base, it's forbidden. So most of those changes, most of those customizations are not allowed. But César Vieira, the architect, in an incremental design way, he defines some possible changes. But what is happening now is much more than those allowed changes. We wanted to know if people would like the tool to be just with the allowed changes, or if they wanted more possibilities. we also had some, I would say, some severe difficulty in interviewing people. I would say that we interviewed 1/3 probably of the people that we tried to interview. Lots of people, when they looked at us and they said, coming from architecture, they wanted to know if we were coming from the city council or from the architect's office. And they often said, I'm not even the owner of the house. No, I did nothing. So they were in a defensive mode, meaning that this also, because this neighborhood is very known in architecture, this is a problem, or they considered it to be a problem. So this question, we wanted to know if they indeed wanted to be controlled or not. And in a surprising way, most of the people said that yes, the tool should control the changes according to specific rules. And then we add something. What more could the tool offer? So in this moment, the tool only offers a limited everything is happening at this moment. Here in Lisbon, everything's switched off, but I think it's going online still. So we wanted to know what more could the tool offer. Some people said the tool is good as it is. Others said that it would be nice that the tool could also enable changes in the interior layout. And others said, this was, I think that on the 12, there was only one person that said that the tool should not present solutions that are forbidden. So our tool is more, enables more than the rules by the architect. And to end, just a brief concluding remarks. So my changes is meant as a way to respond to the issue that customization poses to architecture, and it's aimed at, for one side, to support housing customization that accommodates the changes in life of inhabitants, and on the other way, to support customization that complies with the original architectural language. So those two issues that usually are considered or are at the end point considered to be a paradox in architecture. It can be used as a way of mediating the communication between the architect and users in a participatory design process. And it also can be used as a way to users to express their wishes and by directly designing and co-designing in a playful way. So we conclude by saying that architects need to define identity preserving refurbishment options, and shape grammars look to be a solution for this wish. Okay, thank you very much. I don't know if everything went well on that side. We had lots of technical problems.
So for our second presentation, we will have Wassim Jabi, and I'm not daring to pronunciate the second author because I'm going to spell it wrong. So the title of the presentation will be Topologic, Exploring Spatial Reasoning through Geometry, Topology, and Semantics. And now I invite Professor Wassim to initiate his talk.
Thank you. Am I able to share the screen? Yeah.
We are not hearing you. We are not.
Oh, can you hear me? Hello? Yeah, Pedro can hear me, it looks like. Yeah, everybody else can.
Sorry.
Okay.
You could share now, Professor?
Okay, let me try.
We are not hearing you.
We can hear him.
That's kind of strange.
There's no sound.
Oh, weird.
But Professor has a sound turned on. Could anyone online speak?
Yes, we can
precise
hear
request.
Wassim,
Just
Jabi.
to try if the sound is from us, it's went wrong from us, or Pedro, could you say something?
Yes, yes, we can
Okay,
hear
so
Wassim,
it's
Jabi.
ours.
Não pode ser nada aqui.
Foi isso, deve ter sido por causa daqueles
Pois é,
Vamos chorar um bocado, que
não mexeu nada, estava tudo a funcionar.
não, mas
Quando...
disse que tinha sido um cabo qualquer.
Depois agora não tiramos nada. Can you listen to us?
Yeah, I can hear you.
Okay, so it's our problem. We don't have sound from you. Sorry, just. Quer desligar e voltar a ligar?
Mas será isto?
I'm gonna try without this light. 1 second. Is this any better? Yeah, this should be fine.
Mas o que é que será? Que é isso que eu não percebo. Como é que está o áudio? Olha isto. We see your presentation, but we don't hear you.
Mas o som que vem é daqui, não é?
Para nós.
Não, o nosso alto-falante vem de onde? Vem daqui?
Acho que sim.
Vem daqui. Pedro, can you try it again? Can you say something? Sorry.
Can you hear me?
Sure. Yeah.
Okay,
Again.
no, still not. We see your mouth. Nothing but not the...
It's probably the headset or something that was connected.
I think they muted the sound because there was an echo.
Oh yeah, that's true.
But I don't know how to tell them that.
Maybe we'll type some message here.
Yeah. Maybe.
Posso te ligar e te voltar a ligar, não? Pois, como é que eu ligo isto?
Sorry, we will try. We hear you on our PCs, but we don't hear you in the auditorium. No, there it is.
Não, para lá são 3.000. Nós não sabemos é se nós estávamos a direção de lá.
Terá sido algum cabo?
Não sei, eu estava procurando no telefone.
Oh, is it working?
Yes. Oh,
Yes.
Okay,
they can
so
hear
now
me.
we hear you.
You can hear me well?
Yes.
Excellent.
Yes. Long and
Okay.
so let's start.
Okay. I assume you can see my screen?
Yes.
Okay, fantastic. Well, thank you for your patience. I know it's been a long day. So this paper is about a piece of software that we have developed under the Leverhulme grant. It was a £300,000 grant that myself, Robert H. at UCL, Simon Lennon, Nicholas Wardhana, and Katerina Chatzivasileiadi kind of worked on for about 3 years. So I'll tell you a little bit about it and why we decided to embark on this research project. So this presentation, I will introduce Topologic a little bit, talk about what it is and what it can do. I'll talk about what I mean by spatial reasoning. How do you think about space? And then we'll report on the very preliminary results, very admittedly very small workshop that we did to test the usability of Topologic. And this is the first time we formally did a usability workshop, and we hope to do a much larger one in the future. And then I will conclude with some remarks on what this means, what the workshop results mean, and what Topologic is about and what it can do in the future. But mainly, the main reason we started this research proposal, what we proposed to the Leverhulme, is a dissatisfaction with building information modeling. Building information modeling is obviously a great advance for architects. It has really made the process a lot more rational, a lot more shareable. But we think something has been lost in the process, and that thing is the concept of space. So when we are looking at this commercial BIM software, they kind of force you down a road where you are creating what we call stuff, in a very scientific term for it. Basically the components, the building fabric, the solids, the furniture, the MAP, the windows and the doors. But what they do not encourage you to do is to think about the quality of space that you are creating. And space has been traditionally very, very difficult to represent in 3D modeling systems and computer-aided design systems. So we wanted to see whether we can work on a system that at least has some idea about space and how space relates to adjacent space. So the idea of topology is that things in that environment, in that model, know about each other. The other thing we were dissatisfied with is that BIM models or BIM software, such as Revit, for example, in this case, and at least in the early stages of it, they ask you to create complexity, and then they ask you to derive simplicity out of that complexity. And that we feel is completely backwards to how architects work. We do not create very complex structures, very complex buildings, and then say, okay, now let's kind of distill them down to their essential qualities. But in order for you to do any kind of energy analysis, for example, as you see here, thermal analysis, they ask you to simplify a very complex BIM model. Now, and that is an obstacle for architects trying to do performance modeling in the early phases of design, because they don't have the needed models. But we know that we have them when we are sketching. We know that we sketch very simple volumes, zero thickness walls. Our sketching and our kind of early design is actually very compatible with energy analysis. So why not kind of start with simplicity and then allow software to create that complexity that you need out of it, or to what I call populate your BIM model. And I've said it in many presentations in the past, where I say software is actually getting to the point where they are far better at populating BIM models than humans. We shouldn't be wasting our time as humans putting doors and windows and seats in an auditorium. BIM software can do it for us. So why not focus on the important stuff, which is spatial concepts and spatial adjacency and how things are organized and designed. The third part is the idea of awareness. And this is, again, a dissatisfaction that we saw with a lot of the 3D modeling systems that we were using. On the left side is my favorite one, Autodesk 3D Studio Max, that I have used for many, many years, and I teach my students how to use it even up to this day. But when you create objects like these cubes in 3D Studio Max on the left, and you imagine yourself asking a question of a certain cube, say, cube A, tell me who is your neighbor, who's below you, who's above you, who's to your left, who's to your right. That cube cannot answer that question. It does not have any awareness of what other cubes are around it. It is basically a dumb object. It's just an object in a display list. So Topologic tries to solve that problem by allowing objects to answer spatial queries and topological queries. So what you see on the right is a small exercise that my colleague, or my ex-colleague actually, because he left, Robert Doe, he did with his students, where he was looking at modular architecture. And he used Topologic to kind of try to find the intersection or the shared entities between different objects. And Topologic is very good at doing that. The other thing is that BIM models are basically graphs. What do I mean by that? And I mean that the data in BIM models is actually quite well connected, but the software or the mechanism by which you can ask it questions is always ad hoc. That's why BIM models or BIM platforms rely a lot on add-ins and other third-party software to expand its functionality. But we believe that there needs to be, I mean, that kind of can fall under its own weight to always rely on add-ins and other things to kind of help you. The data is in there, but it is not structured in a way that allows formal analysis, that allows kind of like straightforward APIs that will allow you to get it. So it's always kind of there and not there. But if we have a graph, and Topologic is very good at dealing with graphs, we can do a lot with BIM models in terms of analyzing the topology of it by kind of mining that graph data. So what is Topologic? Topologic is basically a set of classes, object-oriented classes. It starts from, and it represents very, very simple but clear entities, starting from a vertex, which is like just a point. Two vertices make an edge. A group of edges can make a wire. If you close that wire, you can make a face out of it. If you put these faces together and they share edges, you can get a shell. And if you close that shell, you can get a volume, or what we call a cell. And then if you put these cells together and they share faces, you can get something called a cell complex, but they have to share faces. And if you want to combine all of them together, you can get a cluster which can have multidimensional entities in it. It can combine vertices and edges flying around and cells and cell complexes all in one entity. And if the cluster is self-merged, you can still ask about topology. Now, when people see this class, they say, oh, so you are dealing with straight lines and flat surfaces and cubes and kind of orthogonal geometry. And that is not incorrect. Topologic can deal with very, very complex geometry, but it represents the topology of it in very clear ways. So an edge is a connection between two vertices, but the geometry of that edge could be a curve, could be like an S shape, could be very complex, but it's basically a starting point and an ending point, or a starting vertex and an end vertex. And that kind of topological clarity allows you to decompose your design in very interesting ways. Now, in addition to these geometrical or topological concepts, we've added some new things to it. We've added, first of all, we've added, as I said before, the idea of a graph, and we can use graph theory kind of methods to analyze a model that we are creating. We also created something called content and context. So basically, any object in Topologic can have other things in it, other topologies stored in it, very much like the boot of your car, so you can put different things in it. And topologies in Topologic can exist within the context of something else. So for example, a window can exist in the context of the wall that hosts it, the wall that it is on, but can also exist in the context of the room that it is in. So, right, as an architect, you want to think about a window. Sometimes you might want to think about the window and the wall that it exists on, but sometimes you can say, what room does this window or door open into? So you can have multiple contexts and multiple contents kind of connected to each other. And the last thing is the idea of dictionary, and this is where we bring semantics in, is that every topology can have in it a dictionary of random or any number of key value pairs. So you can put the cost of something, the area of something, whatever you want, integers, floats, strings, anything else, you can pack those into a dictionary, and I can show you the power of that dictionary a little bit later. As a software architecture, for those of you that care about that, Topologic is open source. It's available for free on GitHub. It's written in C++ at the bottom level, and it uses Open Cascade. And then there is a C# layer on top of it that enables it to talk to things like Dynamo and Grasshopper. But it is also available as a .NET by itself, and we are working on it to be a lot more platform agnostic, let's say, working in Linux and other platforms. So what does it do? To start with the simple things, it can do regular and irregular Boolean operations. So we know about the regular ones. Those are, we can find them in Dynamo and Grasshopper and Revit and all of those. So you can do union, difference, intersection, XOR. But the irregular ones are interesting, things like merge. So when you merge two cubes, as you can see at the bottom middle one, the result that you get is actually a cell complex made out of 3 cells that are all interconnected. So it's not only kind of the outside volume, but it's actually there are interior partitions that are all part and represented correctly within that topology or within that geometry. And that allows a lot of power in terms of thinking about how you segment a building using interior partitions. And as I said, you can take any cell complex or any topology really, and you can derive its dual graph. So the dual graph of a cell complex, like you see here, like this kind of honeycomb grouping of cells, is a wire made out of the lines that connect the centroids of those cells. But in addition, you can add different things. For example, you can customize this dual graph by telling it only go through the shared surfaces or connect to exterior surfaces. So you can do really interesting graphs that are customized to the operation that you are trying to do. For example, going from one room to the other only if there is a door from one room to the other. The content context and custom dictionaries is a little bit more of an advanced topic, but I'll try to explain it. Some people find it hard to understand how it works. But let me explain it through this image, this example. You have to imagine this example first as being made out of only 3 cells, not so many cells as you can see here. There are maybe 50 of them here, I don't know how many, but imagine them being made out of 3 stacked cells, a blue cell, a yellow cell, and a red cell, right? Blue block, yellow block, and the red block. Those 3 cells I have embedded in them 3 dictionaries, one dictionary for each. One is retail, one is office, and one is residential, right? Retail at the bottom, offices on top, and then residential on top. So these 3 cells have these dictionaries. Then I go and slice these 3 cells. First, I build a cell complex, and then I slice it into the cells that you see here. I take planes, and I slice it up into a lot of smaller cells. Each of these smaller cells automatically know where they came from. They know their DNA. They know where they came from and inherit that dictionary. So I don't have to assign residential units to all these multiple cells, the 20, 30 cells that I have. They inherit that dictionary from the parent cells. And that's the kind of the power of it, is that dictionaries survive and get transferred through Boolean operations. The other thing that Topologic is really good at is spatial and component resolution. And I'll show you a video. After all these kind of images, you will see a video that kind of animates it a little bit. You can explain it. In this case, what we have is we have one cell complex, which is this building with multiple floors. And then we want to impose, that's another operation that Topologic does. We want to impose a kind of a vertical atrium of some sort on it. Now, if you want to impose rather than merge, the atrium should stay whole. It shouldn't have lines and edges inside of it, right? You need a complete volume from top to bottom. So when you bring it in and it goes through this cell complex, it imposes itself and resolves all the edges correctly. So as I show you the animation, keep your eye especially on the middle vertical line, right in the center of that building, and see how it disappears and reappears automatically because of the impose operation. So right there, it starts disappearing and then reappearing. It's a very simple animation, but what is happening is that the impose is actually cutting and clipping all the lines and all the surfaces correctly and creating a cell complex that continues to have all the cells knowing about their neighbors. So you can always ask questions about it. In this second animation, I have, again, a cell being imposed on a cell complex. But in this case, I am asking the surfaces, the faces, to answer a simple question. What two cells do you divide? What is on your left and what is on your right? And the answer determines what color I give to that wall or to that surface. So the first step is I ask the surfaces, how many cells actually do you divide? Do you divide two? Are you adjacent to two cells, or are you dividing only one cell? If the answer is one, take a look at the images. If the answer is one, by default or by definition, this is an exterior surface, right? All the surfaces that are interior divide two cells, but the ones on the exteriors are adjacent to only one cell. So if that is the answer, I color them in red. Now I take all the remaining ones and I ask them a second question. I say, do you divide two offices, two small offices or two small cells, or do you divide a small cell and a big atrium cell, like a big space of some sort? If the answer is I divide two small offices, I color those in blue. And if the answer is I divide a small cell and a big cell, I color that in red. So at every point in the animation that you will see, the surfaces are answering two questions. And based on that question in real time, I'm assigning colors. Or in the time of the animation, I'm assigning colors. So again, the effect is really subtle, but you'll see that as this cube enters and leaves the building, its own surfaces answer the question differently and therefore get colored differently. This animation is very similar. The cell complex has cells that have dictionaries that say I am either light or dark, or 0 or 1. And then I impose this blue axis on it, and then I ask this blue axis to give me back the adjacent cells. So it gives me a selection of dark and light cells, right? They have those dictionaries. And then I say, okay, take the ones that have the dictionary that has a light color in it, and then highlight that in yellow. So as this blue axis goes through this building, you'll notice that only what used to be a light color gets highlighted in yellow. How would that be useful for architects? For example, if you have private and public spaces and you're putting a public access through a building, you might want to know which of the spaces are public, which ones are private, and open the windows or the visibility to them differently based on the answer that you get. In this one, I used try to use space syntax for this. So because we can build a dual graph, we can do graph theory type of stuff, and space syntax is a lot of it is based on graph theory. So in this case, what I have is some sort of a theoretical design of a building, and I'm moving these bars around, and I'm asking every cell to measure its distance, its topological distance to all the other cells in this building. And based on that answer, I am color coding it from dark blue, meaning the longest distances, to bright red, which is the shortest distance. So this is what is called space integration or space centrality analysis. So you can find out which spaces are really central in the building. That's maybe where you put the entrance or the water cooler. And then which ones are isolated that you might want to take care of. So as the design changes, the reply is changing and the color coding is changing. And if you look really carefully into this animation, right inside those translucent cells, you will see the three-dimensional dual graph that's actually doing the computation.
I'm sorry, Professor, you need to conclude, okay?
Oh, right, sorry about that. So we did a usability workshop, We looked at 3 tasks in it: geometry, semantics, shortest path, and topological distances. The first one was about two objects that intersect, and based on the dictionary in each one of them, it creates the height of the intersection. So they did that. This was a very simple example. And then another one where the shortest path between 2 points is based on the volume. So as the volume of the objects change, the path will reroute. And the third one was very similar to that space syntax example. Again, it's looking at topological distances. These users were not very familiar with Topologic. And in general, it was a very positive experience, but they had some difficulty with some of the terminology in terms of what is a cell, what is a cell complex, what's dictionaries, etc. Just to kind of conclude, fundamentally, Topologic expands the pursuit of fidelity to design form to include the pursuit of fidelity of design intent. We have done a lot of kind of realistic representation, in our history, but how do we actually do very accurate representation of our design intent? And that's what Topologic is about. I'm going to stop here. You can read the rest, and you can read the paper for more details. Thank you.
Thank you, Professor, for your presentation. Now we are going to pass to Pedro Veloso, I think, are going to present. Is it you, right, Pedro? Ramesh?
Sorry? Yeah, I'm presenting, yes.
So Pedro is going to present self-learning agents for spatial synthesis. Sorry, it's late. So you could start.
Sure. Can you see my screen?
Yes.
Okay, so my name is Pedro Veloso. I'm a PhD candidate at Carnegie Mellon University. Professor Ramesh Krishnamurti is my advisor. I'm going to present the paper Self-Learning Agents for Spatial Synthesis. The topics is related to spatial synthesis, which comprehends finding spatial solutions that satisfy specific objectives and or constraints. And the situations that mainstream computational techniques are typically solution-oriented. They often use like destructive techniques, and that often results in the distinction between human turns and computer turns in the generative process. So you can see in the image, like designers can create a generative system, and after creating the generative system, they access the input of the system. The generative system generates a result, and they can see the result, maybe change the input or even create another algorithm, run it again. But this solution-oriented approach can be alleviated by partial execution or by efficient algorithms. However, our motivation in this research is to understand spatial synthesis as a form of dialogue. So instead of having this distinction between a generator and designers, we're interested in a setting where there is fine-grained interaction. Computational entities and designers, they can explore the design space together. And this is in the scope of early stages of design, where you're actually using diagrams and you're interested in partial solutions. So our approach is to think about agent-based models. The agent-based models, they use simulation in general to represent certain phenomena. But with that, they provide like real-time fine-grained interaction. They enable that. And they enable the parallel construction of solutions with embedded constraints in the agents. And potentially, they can also enable emergence of forms and emergence of behaviors. But it's interesting is because they allow, with a generative system based on agents, you have access to partial design information. And so there are a lot of design opportunities to restructure the design on the fly. Here are just some examples. This is like a part of last year, we published a literature review on agent-based models and space planning, spatial synthesis, and the things that were discovered after studying the existing models is that typically the models used for agent-based spatial synthesis, they're imported from other fields. So it's not straightforward, it's not easy to adapt them for architecture design. It's hard to tackle like multiple spatial requirements. It's hard to address like how agents deal with spatial conflicts. So in general, designers tend to combine these techniques with destructive techniques, more like conventional classic spatial synthesis techniques for initialization, refinement, to be able to overcome these bottlenecks. Our proposal is to develop agent-based models for spatial synthesis that can solve spatial conflicts, and they can develop custom behaviors for custom architectures. And how we intend to do that, the idea is that we teach spatial agents with reinforcement learning. Basically, reinforcement learning is a branch of machine learning that some people say that machine learning is escaping from the cage of perception because you're addressing a control problem. You're trying to train an agent how to behave in a certain environment. And the base of reinforcement learning is to model decision making. So it uses a Markov decision process. If you see this graph here, it's a representation of a MDP. And the way it works is that you have an agent. So you formulate your environment, your problem, and you put the agent in that problem, and the agent has to take decisions. So the agent is placed on this MDP, and this spatial agent has to take an actions. For example, the agent can be in one of these states, the green nodes, and select one of the actions. This is on the top diagram here. And then the agent sends the information of the action to the environment, and the environment sends back the information of the next state and potentially a reward signal. So you can see here that the agent can select an action, and that action can lead to another state. But also there's like a reward signal telling like, oh, this is good, this is bad. This is how you teach the agent. So the point here is that we use reward signal as a source of learning. So designers can provide a goal saying, okay, this is what we want the agent to do. But you don't need experts to design a grammar or to design like an agent-based model. You're just telling the agents what to do, and you provide like a reward signal, and the agents learn how to do that. So in our prototype, this paper is about a prototype, our first prototype. We use a grid representation. I think it's well known in our field. There are many advantages in using grids. They simplify spatial queries. They enable the use of efficient computer vision, machine learning algorithms. You can encapsulate contextual design information in discrete entities. It's extensible to 3D. You can control multiple resolutions, and it also supports different types of room shapes or packing. And you can see here on the bottom, the left, that we have a representation of our agents. This is a simplified representation. So you can see that we have kind of like a board with obstacles, and each agent is just for visualization represented with a different color. So the agent's a polynomial with no holes. So the agent's like this set of cells that shares edges. And the representation of each agent, this is just for visualization, the real representations on the right. So each agent has like multiple grids with different types of information. So the agent can see the board, can see the environment using a perception grid, but it also has its own like action grid. You can see the smaller rectangle here, it's like a subset of the environment. And it can actually select cells inside that action grid for expansion, for retraction, or it can actually not select anything. And then by combining the simple units of actions, it can generate combos, it can generate like complex behaviors, it can jump, and it can actually move, because as the agent changes shapes, the action grids based on the centroid is going to move, so the agent can actually move using those actions. And the interesting part is that the actions are constrained. There are design constraints embedded in the agent. So the only actions are allowed are the ones that preserve the polynomial with no holes. And you can see like some of the layers, for example, there's a layer of actions tells exactly that, what cells you can select for the next action, for example. We also have types of cells of the agents. We have a mask with the action grid. And we also have representations of our objectives. So in terms of objectives, this like we want the designer to be able to tell the agent, well, I want you to do this. And this is represented in terms of objectives. So our approach is to use certain objective functions to define qualities of the agent. And then as the agent takes a decision, the difference in terms of performance can be used as a reward signal for reinforcement learning. So we define a function f for each of the objectives. So we have, in this prototype, we have an objective related to shape, one related to area, and one related to adjacency. The shapes related to is trying to avoid folding shapes. So you want to have rectangular shapes. If you have L shape, you have one fold. U shape, you have a two folds, and so on. Area is trying to achieve a certain area defined by the architectural brief. Adjacency is trying to achieve adjacency with other areas in the program. I'm not going into details, but we also have like a G function that's actually a visual representation that's related to those objectives. And the reason we have this is because we're using neural network and we want to ease training, and we want to enable designers to change those objectives on the fly. So if with all these elements, now we can take like this representation, and this is the state of an agent. So we take this series of grids, we pass this as a state to an environment, and the agent can select an action, and the environment is going to return the new state and the reward signal, considering our objectives. So now we have everything we need to design our own spatial agents. So we can take an algorithm from reinforcement learning, we can use double deep network, PPO, there's many algorithms available. And then these algorithms in general, if they're model-free, they're going to simulate, especially in random environments. So the agent's going to be placed in these random environments, and they're going to learn how to change its shapes, how to move, how to get closer to other agents in order to learn the good behavior. So what we're doing here is that we are training our neural network to be the brain of the agent. We want the neural network to, for every situation that agent is involved, the agent knows what to do to get to a good configuration. So basically, we have a training step. Also, you can see more details about this algorithm in the publications. But basically, for this prototype, we use composition with the adjacency, area, and shape to provide the reward signal. And we provide like random parameters in terms of area, shape, obstacles, and we train with 6 agents. And then we after training, the whole point of training is that we are doing the computation before the real action. So now we can actually use a neural network for the agent to decide the actions in real time. And we want to see if the agent is able to generalize that knowledge to novel situations that were not present in training. So we can have new environments, we can have different number of agents. And the whole point is to see if these agents, they can actually recover for external intervention and achieve good results, because we want them to interact with designers. So now that we have trained a brain for these agents, we can test on a simple but more realistic case. So in this example here, we have like a simple program of a house. You have like different spaces. Each agent is one of these spaces. You have indications of area. You have indications of connections. And we also have a set of different like sites with maybe with an irregular boundary, one with like central obstacles, one with a stream. And we also add a parametric model. So like instead of seeing a grid, you're actually seeing like potentially what could be like a diagrammatic version of a building with windows and connections and so on. But again, this is not an optimization. Our goal here should train these agents to interact with designers. So what we do is that we train them, and we see in a simulation where they're able to react to randomness to see if they can recover from randomness and generate good layouts. So this is like in one of the environments, you can see that the agents start to populate, and they are able to start placing like bedrooms in this irregular areas, the social portion of the house in the front. You can see in this graph that the agents actually achieve a good performance for all the objectives, and sometimes we add some randomness, but they recover. You can see the randomness stages here with these weird layouts. In this other environment with the stream, the agents start sectorizing the program. You have the private spaces on one bank, the public space on the other bank, sometimes of a living room mediating these two zones, sometimes with circulations. And you can see here, we didn't teach how to do this. We just told them what we wanted them to do, and they learned how to do this in real time and learn how to recover from external influence. So our conclusions that we successfully created a training workflow. The agents are able to generalize We can change the number of agents, we can change the environments, the parameters, and they're able to generate good layouts, good configurations. They're able to explore locally those configurations. And our parameterized objectives were successful. So you can change the areas, you can change the adjacency, you can change the shape, and the agent's going to know what to do to achieve those goals. But what about human interaction? You can see on the right here, me and my friend Jimo, we're playing with this prototype, and we want to sketch, we want to change things on the fly. But right now we don't have that interaction. But in the current stage of the prototype, we are developing more efficient agents. We are adding stochastic policies instead of using randomness. And we are using a game engine, so you actually will be able to move these agents, change this, the configurations, the cells, and so on, and the agents will react in real time. So that's the objective of this prototype. And these are the references for some of the slides that I presented here. And thank you for your attention.
Thank you, Pedro, for your presentation. So now we're going to Ítalo. Are you here? Yeah.
Okay, Maria.
Hello.
Hello.
So you're going to present beam-based airport design project standardization for use of code checking, correct?
Okay. View my presentation. Okay. Can you hear me?
Yes.
Okay. Good morning, everyone. Before starting the presentation, I would like to say that I'm very happy and honored to be participating in this conference. I will make the presentation in English. I will do my best so that everyone can understand the research. If anytime I speak a phrase or word that you or not understand, forgive me. I am the process of improving this language. I will follow the sequence present in the script: contextualization, method, results, conclusion. And in Brazil is the second country in the world with the largest number of airports. Thus, the improvement of the development and the analysis process of airport projects has enormous potential to further leverage investment in this sector. This article investigates the relevance of creating a BIM model guidelines manual considering the interrelationship between the team of airport designers and the team of airport design analysts in Brazil. The use of BIM in the AC industry is affecting with the increasing maturity of users, new types of use BIM are being explored, among them code checking. Veloso defines the use of information in three categories: use of the model, use of documents, use of the data. In the category of use of the model, three subcategories: general use, domain use, custom use. In the domain use subcategory, there is the series 4000, where it's possible to find the specific use for code check and validation. The expression code check and validation is one of several ways for using the BIM methodology. The term can be found in manuals around the world, such as Project Execution Plan Guide, National Guidelines for Digital Modeling, STEBIG's manuals, among other documents. Based on solid and estimate, the use of code checking is complex for general class of rules, namely class 1, 2, 3, 4. Rewrite the classification of the rule, the grid, the amount of data assignment in the B model, as well as the grade the complexity for creating the rules in the BIM analysis software. And according to Eastman, rules verification can be used from three types. This article analyzes to the use of the type of tool based on computer software parallel to the design software. The UZFC is already a reality in this country with great maturity in BIM. IFC has presented itself in open and relatively maturity standards currently supported by the main BIM application in the world. Within the IFC scheme, the model view definition defines the specific sub-elements of the data model. That is the MVD is recommendation for which data and elements the IFC model should include. In this article, the MVD coordination view 2.0 was used. Let's do imagining that the MVD serves a kind of export filter in which it's possible to transpose specific information contained in the FC model. In the past, the design of an airport was designed specially according to requirements of the aircraft that would operate at the given airport, which required a limited problems of needs. Currently, as a result of several factors, such proximity to demand generated centers, multifunctional services, the emergency of the new materials in the construction process, the emergency of new concepts made the design of airport becoming a complex activity. The airport design process based on BIM is defined by the multidisciplinary integration of the project data, its organization at the process involved in this development. Once the authority BIM project exports via IFC to an integrated model in step 1, having been developed, proceed to step 2, in which the properties contained in the EFC model will be validated according to any manual guidelines of the model. If all the verified rules admit the process is complex, outside our report is sent to the team design for review of the project. The methodological process of the research is based on design science research. This research is currently in step 1, construction of the artifact. We hope to be able to proceed to step 2. So, the initial results demonstrate the importance of standards BIM models for airport projects. The image on the right shows the graphic results automatically generated in the solid model checker. For this role, the condition of acceptance was the minimum distance 10 meters between the limits of the envelopes of the aircraft parked in the aircraft yard. The solid model checker identified compliance with the established rule without the need to change the design. Rule 2, this condition for acceptance is of the rules that the width of the service desk is greater than 3 meters. The image on the right shows the graphic results automatically generated in the solid model checker. The SNC automatically identified the non-compliance with established rules, with the need to review the project. What was verified in testing 2 examples was that just as it is important to establish rules for the evaluation of the models, the creation of rules alone is insufficient for the evaluations process to be efficient, with the need for the mods to be organized according to the information present in the EFC properties. It's important to note that the example of rules 1 and 2 refers to class 2 rules. From the moment it's possible to automate a set of rules, whether simple or more complex conceptually, this automation will allow more time for analysis to deal with issues more relevant to the project. The figure shown on the left shows the time and the energy radio that the analyst has in the current scenario based on manual analysis process. At the bottom, in the proposed scenario, the ID of a computing system. Once the modeling guidelines manual has been prepared, it will be possible to subsidize the professional involved in the process, reducing the analysis time, the number of project review, increasing the efficiency of the evaluation process by the analysts, standardization the process among other benefits. Regarding the next steps for these researches, we intend to develop step 2 evaluation of the artifact. In addition to development of step 2, we release the potential of using manual guidelines to support other types of evaluation of airport projects in Brazil, such as being able to standardize the evaluation of item parameters beyond the limit of the airport site, use of manual guidelines for several project disciplines, and the standardization of the evaluation process based on other parameters. Finally, I would like to thank to the opportunity and congratulate everyone who is part of the organization at this conference. Thank you very much for your attention.
Thank you, Ítalo.
Thank you.
Questions are open. We have one in the room. Raise your hands, please, if you want to do a question. Okay. So I'm going to pass. Okay.
First, regarding this last presentation, I had the opportunity to I think the airport. Sorry, I think an airport has thousands of rules that have to be checked, and you only presented 2 or 3 rules to check. And I think that you answer this. It's because the base tool you are using is being IFCs and well, the checkers inside that place. And as Professor Wassim already said something about it in this session, and in the session in the morning we already discussed BIM. it is not good for, it's what I think, it's not good to address the main problems of architecture, so that cannot check if those architectural rules are suitable or not for the problem you are trying to solve. No, but the main thing I would like to discuss is about to know better is the tools from Professor Wassim and from Pedro. First, Professor Wassim, we are very sorry that we could not have your workshop here in Lisbon. I was looking forward to assist and discuss your tool deeper. Well, your participation in Pedro is for me, for my profession, for my research, they are the most important, not in the context of the symposium, but for my research, because they think they are Lego pieces of global construction of design, automation, design technologies for architecture. So I would like to have the opportunity to deal with your tools and to see their possibilities. And I would like to talk later to you, not today, of course, about those tools. Well, the first Professor Wassim, I think we're addressing a syntax of space, not space syntax, because space syntax, the name is very wrong in the terms of language theory, but this is real space syntax and algebra, the syntax of algebra of spaces. And this is a piece that we need to design automation. My question is, I see the potentialities of the tool when dealing with space, but I have another problem. I want to, with your spaces after constructed, we can make many operations of your algebra, but can we get some CAD, have you the step that transforms the CAD project in your space syntax or not? Is it possible to transform the CAD data in your, have you some API or something that can be done? This is the first question. Then it's, well, in the algebra of spaces that you propose, and I think you have many operations. Pedro's is one of those operations with the concatenation of spaces, but with some objective, some goal. They try to get near one of another. So you have also an operation like is operation, or was it possible to introduce this tool in your as an operation of your algebra? And for Pedro, well, I have the same problem: how to organize spaces with a given geometry, how to organize to fulfill certain goals. Well, why agent-based? Because I'm not using agent-based for two reasons. First, agent-based design is not deterministic. We don't know if the result, well, it can final result are several. There are several final results that depends on many factors. It's not the problem does not define the solution in a deterministic way. And the second question is well known in agent-based design is that, well, agents try to optimize their own problems. They have rules to optimize their behavior, tries to optimize something. But that optimization of each object does not theoretically provides not a global optimization of all the problem. Well, each agent solves this problem as the global problem is not optimized. I think you said something about the optimization. I would like to say something more about it. Thank you.
Professor Wassim, would you like to start answering?
Yeah, sure. Apologies if I did not understand all the questions. The audio was a little bit difficult for me to understand, but I think the first question was, can we, using Topologic, can we bring CAD data, can we bring BIM data into Topologic and use that, kind of like reversing the arrow? If that is the question, it's a very, very common question that we get, because a lot of the architectural kind of firms that use Topologic, they look at it and they say, oh, well, we already have a lot of BIM data. Now we need to bring it to Topologic to kind of do analysis. How can we do that kind of transition? And there is no clear answer to that. We have done some translation back from Revit to Topologic, but this almost like goes against the DNA of Topologic. The whole research proposal was, you need to change how you do your work. You cannot immediately start a project by saying, I'm going to put my foundations and I'm going to put my walls and my windows and my doors. This is just the wrong way to do architecture. This is not how we did architecture when we were using pen and paper. And BIM systems are forcing us into an unnatural way of doing it. We want to do strategic, conceptual, spatial, topological, semantic type of design, and then use the tools that are built into Topologic to what I call thicken the conceptual model into a BIM model. And we have tools to kind of, or methods to do that. And we are working on more methods to create, let's say, IFC files or Revit files from a conceptual model. If I can be reminded of any other question, because I don't think I got the second part of it.
If in your algebra, there is a tool that concatenates spaces in an optimized way.
So we have done a lot of work on, I really enjoyed Pedro's talk, because if you go back to our EKD paper in Porto last year, we used Topologic and combined it with reinforcement learning for fire egress. So we had agents inside our cell complexes, which were like a building, and they are trying to find the fire egress on their own. So you could put the fire egresses in different ways, and it will find them. We have done a lot of work on optimization, especially with connecting to thermal simulations. So thermal energy with OpenStudio, we have connected Topologic to OpenStudio through Topologic Energy, and we have done it through genetic algorithms and all of that. So Topologic is not just a kind of like a static kind of modeling system only. It's really like a foundation that is very, very open, that you can build more domain-specific software on top of it.
Pedro, would you take the word?
Sure, yeah. I'll start with the second questions. The first one I'll have to review. I didn't understand completely, but I think the question was like, if the agents are solving their own problems, how do I get like a global solution? How I can actually generate like an arrangement that's thinking about like global objectives, for example? I think this is a great question. Each agent in the prototype is not only a space, but whenever you assign a certain like brain to this agent, it becomes like a design entity. It's participating in the design process. That's one aspect that I think is interesting by itself. But also, if you think about as a as an optimization, if it's global, if it's local. The agents, they cooperate. If you think about adjacency, one of the objectives, at least in adjacency, you have two agents that they need to figure out how to solve their own problem, but they also need to think about the other agents. If each agent just tries to solve its own problem and doesn't even care about what other agents are doing, there are some methods that they're greedy, and the agents only trying to achieve that. It's hard to get to a solution. Actually, in this method that I'm presenting, the agents are able to cooperate. The agents, they have limited information of the environment, but we try to provide as much as we can. But they are trained to cooperate. They are trained to understand how they are not blocking other agents, how they can actually move to help other agents too. I think that's a key aspect of reinforcement learning, multi-agent reinforcement learning. But with that said, I don't think that's like the solution for all the problems in design. I mean, this is like an approach that I opted to use for this prototype. And of course, there are certain problems that are harder to solve with agents, and certain problems that are easier to solve with agents. So then it depends on like on the design problem that you're trying to tackle. If you can remind me the first question, I can try to answer that one here.
I don't remember. Oh, I said it was non-deterministic.
Okay.
It's not a con. There are non-deterministic languages that are very useful. Well, Portuguese and English are non-deterministic.
You can speak in Portuguese too.
Okay. So, everything is short. Everything.
I'll just quickly reply to that. Like the agents are not, there's a lot of randomness, so they're not deterministic. And you also can teach the agent to use like stochastic policies. So you're never getting to, not never, but like you're probably not getting to the same solutions for the same inputs or interactions.
So is there any other question? Just one more, because we really have to finish this session. We're running late. No one? I think everybody's tired. So I think it was brilliant, a brilliant session. Thank you very much to all of you that stayed with us until this hour. And thank you for the presence in the room, and see you tomorrow. Hope to see you all. And in Portugal, have a nice night. Okay.
Thank you. Bye.
So,
Since I know last panel had some technical problems and we were delayed, but I'm tired also.
Yeah.
Usually technical problems come when we are tired. So something went.
Yeah.
Yes.
All of a sudden everything closes.
Yeah. Go away. Just go away. We are fed up with you.
It was caused by you taking off the brain was stable.
Yeah, I don't know. Sorry, my presentation.
No, okay.
The content of my presentation